Welcome to Pharmaceutical Calculations, a Conceptual Approach, Lesson 15. Finally, in today's lecture, we're going to describe the methods of alligation for mixture problems. Now, today's objectives is to describe, understand, and apply the methods of alligation medial and alligation alternate methods in mixture problems. Now, let us start with the method of alligation medial. This method is quite simple. It is used always to determine the concentration of a new solution of known quantity that resulted from mixing two or more solutions of known concentration amounts. So in this kind of problems, we are given everything except the final concentration. Now the rules of the methods, or the steps of the methods, are: first, you need to calculate the amount of drug in each mixture and add them up to determine the amount of drug in the final mixture. And now that we know the mass balance equation, this is equivalent to V1C1 plus V2C2. That would give me the mass of the drug in the final mixture. In Rule 2 or Step 2, you calculate the total volume of the resultant solution. So that would be V1 plus V2 equals to Vf. The final rule, or the final step, is to divide Step 1 over Step 2. But now that we know the mass balance equation, it's very easy to determine the CF by dividing V1C1 plus V2V2 over Vf. Okay, so there is no reason to memorize these rules if you just go ahead and use the mass balance equation. Now let us now move to the alligation alternate. So this is a much more complicated method. It does bother a lot of students because of the way it is described and the empirical nature of it. So this method is used to calculate the volumes of solutions that are combined to form a mixture of the desired composition. So in these cases, you are given the concentrations of the initial solutions and the concentration of the final solution. You are also given the volume of the final solution, and you are asked to calculate, let's say, the V1 and V2, the volumes of the two solutions that are to be mixed to make a solution of a desired concentration. Now, these are the rules of the methods that we can describe them immediately in this slide. So to the left column here, you write the concentrations of the initial solutions or mixtures. And in this case, we are describing the method for a two-component composition mixture. Okay? Now, C2 could be higher than C1 or the other way around. CF is placed in the middle of this table and is the concentration of the resultant mixture. Now, you can calculate the parts of C2 by subtracting CF minus C1. That will give you the parts of C2, or the mass of the mixture 2. Similarly, the mass of mixture 1, or the volume of solution 1, is calculated by subtracting C2 minus CF. Okay? The total mass of the final solution is the addition of these two, as is shown there. Let us apply this method in example 6-7, so we make sure that we understand the method. Now here, we are to mix two solutions, 70%. We are to mix two solutions, 40% and 90% IPA, to make half a liter of 70% IPA. And we need to calculate the corresponding volumes of these two solutions. So first, we tabulate our concentrations here, and I've placed the 90% to the top, 40% to the bottom. 70% is the CF, and I'm determining the parts of volume 2 of solution 2 here. Okay, so this is my solution 2, by subtracting 70 minus 40. So that would be 30 parts of V2. Parts of V1 is calculated by subtracting 90 minus 70. That's 20 parts of V1, okay? The idea here is to disregard the units and just make sure that your number here is positive. Now, 30 plus 20 is 50 parts, and that's the parts of the final volume, which is 0.5 liters. So now you can go ahead and make a ratio. This is what we have here. So 50 parts is the VF, and that's equal to 500 ml. 20 parts of V1 and 30 parts of V2. So just cross multiply here and determine V1, which is equal to 200 ml, and V2, which is equal to 300 ml. Okay, so this is how you approach this problem using the alligation alternate method. Now, let us just work up algebraically this method to see if we can derive any formula and avoid using these columns and arrows that go left and right and cause confusion. So the parts of V2 and V1 are determined as it is shown from equation 628 and equation 629, right? But we know that VF is equal to V1 plus V2, so I will substitute those two there, and I end up with VF is equal to C2 minus C1. Now, if I multiply and divide 628 by C2 and equation 629 by C1, I end up with these two equations. And when I carry out the algebra and I substitute VF is equal to C2 minus C1, I end up with the mass balance equation. Okay? Therefore, undoubtedly, the method of alligation alternate is implicitly using the law of preservation of mass of the solute and, of course, of the solvent. So whatever you can do with the alligation alternate method, you can do much easier with the mass balance equation. Now, let's go one step further. Let's determine the algebraic solution of volumes. So starting from our mass balance equation, these are the two mass balance equations we have. Substitute VF, okay, for V1 and V2. So this is what we have there. Carry out the algebra. Now here you separate the variables. So I moved this part to the left, okay, and I took V2 as a common factor, and I moved V1 C1 to the right, and I took V1 as a common factor. Now I have this equation here. The only solutions that will make the above equation to be always true is when V1 is equal to this part and V2 is equal to CF minus C1. So this is how the mathematicians 300-400 years ago, and that's obviously my hypothesis, ended up with the empirical method of alligation alternate. I strongly believe that they did have in mind the mass balance equation. Of course, they didn't perhaps call it mass balance equation, but they did have it in mind. And when they solved it, they came up with this equation over here. And the only solutions that would make this equation true was V1 being equal to C2 minus CF and V2 being equal to CF minus C1. Now, when you go ahead and substitute, we know that VF is equal to V1 plus V2. Substitute V1 and V2 on this equation, and you end up with VF equal to C2 minus C1. So our conclusions here is that the three algebraic volume solutions are part of the mass balance equation. And they can be determined by just taking the difference between the concentrations as it is shown here. So there's no reason to remember these arrows again, confusing arrows. However, we do have perhaps an issue with the units here. So if I just go back one step, so I'm coming over here in this equation again, okay. Now here you can see that the left part and the right part has no issue with the units. These units here will cancel out with these units there, okay? But because V1 is expressed in terms of V2, it is preferable to describe the units of the volume as parts of the total, okay? Simple as that. So if you use this method, the V1 is going to be C2 minus CF, V2 is going to be CF minus C1, and VF is going to be C2 minus C1. Simple as that. Now, of course, no need to follow obscure rules anymore for two-component mixtures. But why bother memorizing more equations now? Why don't we just use the mass balance equation for two-component mixtures? Now let's take a look at the alligation alternate method for three-component mixtures. What would be the complication there? Obviously, now the rules are much more complicated, and they are written maybe in 6 steps instead of 3 steps. But let's best go and solve an example. It's just easier to understand how to do it. So here, we have seen this example in example 6.8, I believe in lesson 14. So we are mixing 5%, 45%, and 95% alcohol solutions to make 1 liter of 65% alcohol solution. So the way we work this problem using alligation alternate is to write our concentrations of the given solutions to the left. And make sure you write them from bottom to top, increasing concentration. So I have 95, 45, and 5. My resultant, the concentration of my resultant solution is 65%. And now to determine the parts of V3, since this is basically here C3, this is C2, and this is C1, okay? Since I can make 65% by mixing 95 and 45, or mixing 95 and 5, then I subtract these two, 65 minus 45 and 65 minus 5, and that will give me the parts of V3. For the parts of V2, I subtract 95 minus 65, and the same thing for the parts of V1. Because 95% alcohol is the only solution that is higher than the 65. Now the total parts is 80 plus 30 plus 30, which is 140 parts, and that would be 1000 ml. Now I'm ready to set up my ratio. So 140 parts is equal to 1000 ml. 80 parts is how much of V3, just cross multiply, and 30 parts is how much of V1 and V2. So I end up with these numbers here. So my V1 is equal to the V2 is 214.3 ml, and V3 is 571.4 ml. Now we have seen this solution once again before in lesson 14, and we called it a special case because we started by setting up V1 equal to V2, substituting that on a mass balance equation, and ended up in these two solutions. But as I mentioned before, that was a special case because in reality we have an infinite number of solutions. This was just a special case. Okay, so let's conclude our lecture today about alligation alternate. What are the advantages? Well, it offers complete solutions only to two-component general mixture problems. Okay, they don't have to be mixture composition problems. They could be other problems too, but it's only good for a two-component mixture problem. Regardless of its complications and the multiple limitations, it offers a shortcut to the skillful. And what I mean over here is that it's quicker because you end up with smaller numbers. That's the advantage that I'm referring to here. It's not the real advantage, but smaller numbers may be handy, right? However, as a disadvantage is that it provides incomplete solutions to either two-component mixtures. We just saw the three-component mixture composition problem. It only gave us one answer, and the solver didn't even know that there are multiple solutions. There are an infinite number of solutions to this problem. It only gave you one, that single one. So the question here I want to discuss is like, what if I don't have the volumes of, what was the numbers, 214, I believe? What if I don't have 214 ml of V1 and V2 of these two solutions? What if I only have 100 ml? What am I going to do? You have no idea because you cannot provide any other solution to this problem. The most important disadvantage is that the allocation alternate method fails to identify the domain of all variables, and therefore you cannot plan your experiment. You don't know the permissible values of these three volumes, so you can plan your experiment. Okay. Furthermore, the empirical steps are very confusing to the student. It's very difficult, it's very hard to remember the arrows. It's very hard to understand why would I subtract concentration and assign units of volume. That's very hard. And because of these obscure steps and these confusing steps, the method does not encourage analytical thinking. However, I would encourage you to understand it and use it if you have the time. Priority, though, it should be the mass balance equation. So finally, I have included two problems here, which are mixture composition problems. Try and solve them with alligation alternate and using the mass balance equation to see the difference. And one more here that is not a mixture composition problem. We have solved it in one of our previous lectures. Now try to solve it using alligation alternate. And of course, this final one, which I'm gonna let you decide which method to use. But they are very nice problems, and they are commonly used in NAPLEX exams. So at this point, I would like to thank you for your attention. Until next time.